Now, good afternoon and welcome to today's lecture. And we're going to build from the previous week. We're going to build from the previous week. I posted some content. I don't know whether you went through them, but it would be very good if you did went through them, because our foundation is going to be borrowed from there. Our foundation is going to be borrowed from there. So yeah, it would have been, it's going to be great if you went across the content. Now, for today, I want us to dive into a special type of semiconductor, or rather a device that been developed courtesy of the properties of semiconductors, and it's called a diode. It's called a diode. Now, so on the slide there, you can see quite a number of images that present how widely this device is used in most of our electronic components. So they are of very different types, but all of them find their footings or their foundations from semiconductor theory. Okay, all of them are generated from semiconductor theory. And of course, I'm sure you know the history of how semiconductor have indeed revolutionized how computing is done, all through to integrated circuits, the ICs, transistors. Okay, so it's really changed the way computing is done. You talk about the memory storage, that concept definitely comes from the ability of transistors. So this is one of them, and towards the end, of course, we look at transistors and briefly introduce amplifiers as we finish up. Yes, so we'll be trying to pick up what was there last week and bring it on board as we move. Maybe some did not go through the manual, so we'll pick up as we merge them together. Okay, so these pictures or images represent how diodes are applied in computing or other electronic devices. And I'm sure some of them we've had them by ourselves. Okay, so there are quite a number. That do exist. Now, so let's proceed and to what these diodes are. You let me know if my slides are visible or not, so that I can find a better way to either make them more visible or do the necessary. So you let me know depending on your view from your end. Now, so diode finds its footing from this gentleman here. Mr. Ambrose. So you can see how long this has been in existence. Years and years and years. Okay. So it is a two-terminal, device. So from diodes is where we get amplifiers. And when you hear about an amplifier, this is an application of transistors. Okay, there's an application of transistor. So it is from diode that we build a transistor, then it is from a transistor that we modify to use it as an amplifier. Okay. So among the applicability of diodes and its related technologies is rectification process, voltage regulation, and of importance to us is the rectification process, because computer science and IT, you don't go into deep electronics the way electrical engineers will go into that, or electronic engineers. So ours is only on the face value, limited to a very tiny domain. Okay, so the application of diodes as a rectifier is going to be a very, very important aspect of for us. So development or construction of diodes, and this is where we do a recap from your end. The P-type and the N-type materials. These are basically materials that come from a combination of several elements, generally from the periodic table, okay, to form a new structure that gives rise to either P or an N type. What is very important is that here majority charge carriers are electrons. Here majority are the holes. Okay. So in semiconductors, it's a bit interesting because both the two should support the process of current flow. Okay. It is unlike maybe when you talk about conductors, copper and the rest, where it's only the electron that is responsible for that. So within the periodic table, the group that is assigned the role of semiconductors is group 4. And we have two materials that are frequently mentioned. That is silicon and germanium. Okay, so these are frequently mentioned most of the time. Okay, so it's these two materials that you combine with other materials to give you an N or a P type. So from bonding or from the previous content that I had issued, if you want to get excess electrons, then you're supposed to use a donor. If you want to get excess holes, or rather you want to get deficiency of electron, because that's what a hole is, this lack of electron then you use an acceptor. Okay. So depending on which element you chose to use, it will give you an outcome that is either P or an N-type material. Now, the whole process that I'm trying to talk about is basically interfering with the nature of silicon or the nature of germanium. In other words, you're adding impurities. Okay, you're adding impurities. That process of adding impurities gives results that is referred to as an extrinsic semiconductor. So that is a semiconductor material that is not in its pure form. The pure form is called intrinsic semiconductor. Okay, so adding impurities into pure semiconductors to generate new materials is called doping. Okay, it's called doping. So it's upon you, depending on what you want to look at or what you want to come up with, to decide which elements are you going to engage. Okay, so circuit symbol of a diode is this. That's a circuit symbol of a diode, meaning on this far end, majority are electrons, on this far end, majority are holes. And this maps directly to the P and the N type there. So this is symbolically what we use in symbol in circuits as the symbol for a diode. But now in electronic circuits, we have these ones, these different structures here that together with the pictures that I was showing you the other side reflect what type of diodes are used. So I've just explained this concept. Now, through that formation process, if you bring those two elements together, or those two semiconductor materials, then two very important terms arise. A layer or a region called depletion. This is a layer that is neither full of electrons nor the holes. It's a layer that is depleted of charges. It doesn't have a charge, whether positive or negative. Okay, that's why it's called a depletion region. On the other hand, junction voltage, at some point we'll call it the barrier voltage, is as a result of electric field strength that is developed at this particular region here. So if an area is depleted of charges, then it has what we call ions. It has what we call ions. So that's the structure there. So you have your P here. You have so this is the layer that we are talking about. This part here. Okay, that's the layer that we are talking about. So of course the P and N will take different forms. But now there's an introduction of a new terms here. These terms here refers to the terminals. Okay, refers to the terminal. So when you bring the two N and P type, later when we'll be looking at transistors, we'll introduce these terminals here. So don't worry about them. Okay. So the zone that is we were calling the depletion region is as a result of electrons trying to cross over to P and holes trying to cross over on the other side, just based on the basic law of charges, that like charges will attract and unlike will repel. So through that particular process, that zone will develop what we call the barrier potential or the junction voltage that will prevent any further flow of electrons to either side of the circuit. That property of the junction or the depletion region to stop the flow of electrons, gives the diode its application in electronics. So at the end of all these processes, the P and the N materials have what we call some electrical imbalance. Okay, meaning some electrons have penetrated, some holes have also penetrated on the other side, or positive charges. Now that process creates what we call an electrical imbalance. And I've mentioned that property alone gives diode its application in electronic devices. We're going to see how that is important. But for now, understand how the depletion layer is formed. So we talked about this one briefly. Electrons move from the N type to the P type. that results in the disappearance of the holes and electrons at this particular junction. We've talked about that. I've talked about the electrical imbalance. And that particular potential difference between P and N is what we call the junction voltage or barrier potential. So I'm trying to pause so that maybe if there's somebody who is putting down some notes, you can you don't get lost. You can still follow what we're doing. If nobody's taking notes, you can also tell me so that we move a bit faster. But of course, it will be difficult to reach a consensus whether there is nobody taking notes. We are not in a physical place, so we'll not be able to know who is taking and who is not taking. So we've mentioned the barrier potential or the junction voltage. So I mentioned that as a result of the ions that are left back in the process of holes crossing over and electrons crossing over and recombining together, that electric field strength that is built there results in that particular voltage that we are talking about. Okay, so how do we overcome that to allow electrons to flow through? And what is the essence or what is the benefit of overcoming that voltage that has been built there? Now, one, when diodes are manufactured in the industry, okay, they have that property naturally. It's a natural process. And the balance that is being created by the voltage, junction voltage there is also a natural process that comes out when those two are built together. Of course, now the strength and the weakness of the barrier potential will depend on the level of dopings that was done on N and P materials, that particular energy or the number of charge carriers that are present. Okay. Now, so to use a diode, as I mentioned, one in rectification process, which is one of its major applications, then there is need for us to bypass that potential. If diode is going to form part of our circuit, all our circuits must allow a complete flow of electrons. That is when we have current flowing, because I'm sure there's no electronic material that will work without current flowing. Okay, so that is the essence. So if diode is going to be part of that material, that electronic device, it must allow current to pass. So how do we do that? That's when we bring on board the process of biasing. To bias, to influence a process out of the scope of its natural development. Okay, out of the scope of its natural development. So you bring something on board to change or alter the characteristics of the natural process so that you achieve process A or process B. Okay, so there are two types of biasing: reverse and forward. Reverse is not effective for us. Forward is. Let's see how the whole process is done. So we've talked about this. So this biasing we are talking about is done by introducing an external voltage supply. So in basic terms is that if you do a reverse connection, then it's like you've connected that particular circuit in the wrong direction. Basically that. Therefore, we'll have no current flowing. If you do forward, the current will flow through. So the polarity of applied voltage causes the charge to flow through the diode. And I've said in that process, we have current. So that's the proper connection. This process, the polarity of the applied voltage, that is the external voltage, will not give us current. It will give us current in very small amount. We'll call it leakage current, reverse current, saturation current. These are current that are not flowing because the operation is successful, but now they are things they are as a result of other external elements like heat, okay, too much heat, and so on. So that current is not desired that comes out of the reverse biasing for the purpose of what we are talking about. In the industry or in the electrical and electronic processes, they'll explain to you why reverse bias is also required. Okay, but for us, we're not really interested in a scenario where the current is not going to flow. We only want to understand how diodes can be used in maybe in computers, so that we understand the basic principles behind the motherboard, the power supply unit, and so on and so forth. Okay. So that means that if it is a reverse, if it is a forward bias where there is current, then it means if we have a PN material here, then the voltage, okay, sorry, let's draw a big one, PN, then the voltage that is going to be connected from there and the one that is going to be connected there, this should be positive, this should be negative. So this is the external voltage supply. Okay. So this will not do the opposite. It will not attract the electrons here because they are opposite charges, not opposite, but like charges, they'll repel one another and push through the electrons here. Okay. So this can only happen if the external supply voltage is greater than barrier potential or junction voltage. We'll call it VB in our calculations in the next topics. Okay, barrier potential, VB, where B is a subscript. External supply voltage, we can call it EMF source, or we can call it VS. Okay, so these are terms that are symbols that we'll meet quite often. So when VS is greater than VB, electrons can be able to flow and current can be realized in this circuit. Okay, so that is why when a diode is fitted maybe into as part of an electronic component, then there is need for you to connect that component from the external power supply to be able to necessitate or to be able to influence this process for current to flow through. Of course, diode, the work of diode is not to block current. Diode is going to be stabilizing the current. That's what we call rectification. From an AC to a stable DC, that is, our devices can consume. Okay. But now, for you to do that, you have to go against, or you have to influence the natural property of a diode to allow current to flow through biasing. So this is what happens through the process that I've just explained there. If you plot a graph of current and voltage in reference to what a diode is able to do, then your graph will look like what is presented there. I hope you can be able to see that. Now, so based on the biasing techniques that we've mentioned, we have two regions. We have the forward region and we have the reverse region. So meaning a diode can operate in those two regions, but with a lot of risk. Okay, with a lot of risk. Now, so there are two elements that are very important in this process. There's what we call reverse breakdown voltage. There's what we call the knee voltage. Okay, the knee voltage. So what happens is that if the diode is operating in the forward region, the diode is operated in the forward region, it will take some amount of voltage from the external supply to overcome the barrier potential, VBE. VB, not VBE. VBE will come in transistors, VB, okay? Now, once the VB is overcome, we expect that the flow of current in that region, the forward region, the flow of current in that region, the forward region, will increase instantly with very little increase in voltage. So from mathematics, if this is the value of current and this is the value of voltage supporting that, then you can see the proportionality there, or the ratio that supports that direct proportionality. There's a big gap on the amount of current and the amount of voltage. Okay, so once we overcome the knee voltage, this knee voltage is the barrier potential voltage, then we don't need much voltage to continuously or keep on operating. The knee voltage, because it is something that is as a result of the internal properties of germanium or silicon materials, it is estimated at 0.3 V and 0.7 V. So this is to help the industry manufacturers be able to determine how much of the external voltage do we need to overcome the knee voltage. Then from there, we don't need so much voltage to operate. On the other hand, if we operate on the reverse direction, of course, I need to mention that this current I was talking about here, we call it forward current, okay? We call it forward current. So if you operate on the other region, we'll realize this type of current. I mentioned leakage current, saturation current, reverse current, and so on and so forth. Basically, they mean almost the same thing, although their sources, if you go into details, will be different from one another. Now, this region has what we call a reverse breakdown voltage. In other words, if you do the reverse direction, the diode can withstand only up to a maximum of a certain amount of voltage. If that voltage is pushed past that, then we say you've gone past the allowed or minimum reverse voltage. Therefore, what happens? The diode enters into reverse breakdown voltage, a process where the diode is no longer in control. In other words, the diode is no longer working. It cannot really be able to do the right or do the necessary thing. So at that particular point, the amount of current that is being generated will sharply rise. This type of current that is rising is not the forward current, but it is the reverse current. At this particular point, the diode is no longer in proper use. Okay, so when we'll be talking about power dissipation, we'll say there's amount of power that the diode can dissipate without being destroyed. So such amount of voltage, if allowed through, then such diode is considered destroyed. So I've mentioned these ones, that's why I'm just showing them, maybe for those who are taking notes. So let's look at the application of diodes. Application of diodes, this one is going to be very short. So we've known what it is and how it is made. So number one, I said was rectification. So we're going to explain some of the major ones later. So there is sensor, signal, voltage regulator or voltage clipper, So for those of you interested in telecommunication, this type of applications will be of interest to you. LED, light emitting diode, an oscillator in circuits, in oscilloscopes. There's a tunnel diode, Varactor diode, in tuning, light sensors, in remote control unit, photodiode to support their infrared protocol, laser. Okay, so those are areas where diodes can be used. And I've said that the major application that we want to look at include, now, of course, these are how the power supply section should look like. Okay. PSU, power supply unit of an electronic device, should look like that. So diodes plug in here most often. Okay. Find itself here most often. So that is just basically a snapshot of electronic device. I'm sure we'll not be able to see that very well. Maybe you can have a look at it from the notes. You'll not be able to see that very well. So we all know what this one is. You know where these wires are going. Okay. If not, then it will be taught in maintenance. Is it? It's called PC maintenance. I think so. Okay. So this is what I was mentioning. That's what we call a power supply unit. So from here, from the left is a transformer, which will do the necessary step up, step down, depending on the number of coils or the number of turns on the primary or the secondary windings. Diode will do the rectification, then into the filter, voltage regulator, and then into the load. So the content should pass through here before it can get to our electronic device on this end. Okay. So the transformer, I've said what it's supposed to be doing. So there are a number of items that there that from electrical perspective, issues of ripples, ripple effects, and okay, so those ones you can study them. You need to understand waves first. Then you can be able to get into those concepts of ripples, effect, and the formulas. So those are what I've talked about the waves. Our interest is not really into that. Want to look at rectification process. So that's the type of rectification that exists. So that's where diode is implemented in big. So there's half, there's full. So full is in 4 diodes and 2 diodes. So bridges are 4 diode rectifier. So what is currently working is actually full wave rectifier because it provides a complete DC output that is consumable with electronic devices. Okay. So that is what a half wave is supposed to be. You look at the DC output there, then you realize that it's not complete. Okay. Meaning, because we are using one diode, we are only in a position, or we are only able to convert 1/2 cycle. The other half will not be able to be converted. Okay. So that's the same thing here. So one part is passed, the other one is blocked. Okay. In other words, 1/2 of the cycle, the diode is forward biased. It allows current to pass through. The other half, the diode is reversed and does not allow the flow of current. So its name is derived from the concept of half the alternations passing through to the output. So in other words, we are using one diode. That's a major important thing there. So that's the conditions. And that's the possible diagram. So our single diode is here. This is the source, AC source. So the waveform, of course, remains the same way. So full wave rectifier. And mention that the only difference is that it has two diodes, and therefore we'll be able to conduct or produce what we call ripple voltage across the resistor from both directions. So when one is reverse bias, the other one is forward, and the opposite happens. Okay. So it can either be in two diodes or in four. So four is what we're going to call bridge rectifier. The only difference is that the amount of output DC voltage on bridge is twice the amount of output of DC voltage in two diodes. That is as a result of the additional two diodes on the bridge that ensures that the incoming AC voltage is not split into two, as it happens with with the two diode full wave. Okay, where the incoming AC is split into two. This one, it's not split into two, it's pumped into both directions as a whole. You can look at the operations. So you can see the two diodes. So diode 1 will allow current through in the positive half cycle, and diode 2 will allow in the negative half cycle of the AC. Okay, so as we come down, so here diode 1 will be conducting, diode 2, diode 1, diode 2, and the process continues, and then we get an output voltage that is similar to this. See our transformer here is center tapped, okay, dividing the incoming into two. So this is just earthing, okay, excess voltage or electrons to the ground. This is the source, AC source. So that is just an explanation, further explanation on how that process is going to go through. So that's negative alternation. So it's now the turn of D2 to conduct. Now the turn of D2 to conduct. So this, the diode will always work together with the transformer. Maybe just as the way I'd mentioned earlier, the component of a PSU, power supply unit. Okay, those four things will always work together. So for you, those who are drawing, you don't need to draw several diagrams. Just draw one and show directions. When the positive attenuation alternation is going through, which one is conducting. When the negative alternation is going through, which one is conducting. You don't need to draw the several diagrams that are presented there. So if you put the waveforms of the output, then you realize that it's now a continuous output. I think we've explained that. So let's look at bridge briefly. That's the device. So what's the difference? Is the number of diodes here. So this presents a full DC signal from the incoming AC sine wave. Okay, so from your maybe physics of Form 3, Form 2, somewhere there, you know the primary and the secondary windings of a transformer. That's ratio here. I'll not go into that. Okay, you know that ratio there. So it's only the number of diodes there and the way it's been tapped into the transformer. Okay, the mode of tapping into the transformer. We're going to see that in the next diagram. So for those who are drawing, you can pick that diagram. Then the subsequent one just show arrows where necessary. So during the positive half cycle, the circuit extraction should look like this. The circuit extraction should look like this. Pay attention to that. Pay attention to that. So that will dictate which diodes are conducting. So that's an ordinary rule of current flow. It takes the next path, BC. So it moves from point C to point D, and the current is experienced through the resistor, the load resistor. I think you still remember the difference between R and R. Okay? The smaller R and the bigger R. So that's a complete cycle. So once it goes, not complete cycle, one complete half cycle, okay? Then it does the other half cycle, E to F. D2 is forward, conducts. Remember, from point okay. So that's the summary of how those two diodes will conduct. They'll conduct in pairs. Okay. So when D3 is forward biased, on the positive, D1 is reverse, and D1 will take the negative half cycle. Same happens to D2 and D4. And the final output stream is a continuous full DC outcome. So you can maybe as part of your reading assignment, just read through the comparison, the advantages between, not advantages, but the comparison between full, that is 2 diode, and full, that is 4 diode, which is in essence a bridge rectifier. Compare the advantages, just compare the advantages. There are only 2 or 3 advantages in terms of cost, in terms of the final output. Just have a look at that. So up to this particular point, I mentioned that other components that surrounds a transformer and a diode is a filter and a voltage regulator. Okay, so at this particular point, just have a view that a filter is charged with the responsibility of reducing the ripple in the input waveform. You can have a look at ripples if you're interested into pursuing further components. But for our class, our concern is on diode and transformer. Okay, so any question as far as the whole process is concerned? Okay, so maybe something that I should explain before. The slides that I'll be posting on for you. Okay, sometimes I'll post the slides with just additional content that for those who are interested can help you reflect and maybe read further. So like for instance, these slides that I have here, I'll use it to teach a different group that learns these other things, the voltage regulator and so on and so forth. So I'll not split it. I'll just post it for you guys the way it is. But for you, know that the syllabus is up to rectifier. That is diode. Okay. The rest you can read if you're interested in reading. Is not really, but very, very important. Okay. Like Zener is a special type of diode that is used in voltage regulation. So you can as well look at what voltage regulation is all about as a student who is interested in electronics. So that when we open up after COVID, you can visit the engineering lab and look at some of these things. Okay. Yes, the same happens with the content I'd given you last week. Superconductors. Superconductor is not part of your syllabus, but is an area in electronics that is coming up. Is not part of your syllabus. So even if you did not understand a number of things in superconductors, don't worry. Okay, your content was semiconductors that builds into diodes and the other things that we look at. Okay, so next week, if we meet, we'll look at transistors. What is a transistor? It is a N, it is a P, it is a N. It is a P, it is an N, it is a P. Okay, so this is where we get our base. Not the base. Base will be somewhere here. Hapa katikati. We'll get our collector here. Somewhere here. And finally, we'll get our emitter somewhere here. So this three terminal stuff is what we call a transistor. And it has a wide range of applications, from a switch, from an amplifier, to contributing to the storage within a computer system, the memory, the zeros and ones, okay, and so on. So that's what we'll look at next week. So unless there's a question, I will comfortably allow you guys to enjoy your weekend. will comfortably allow you to enjoy your weekends. Shepkurui Naomi, is your account working now? Your account exists. I don't know why you cannot be able to log into it. You let me know if it is working. Helen, you're a new student or a continuing student? And Bryson, is it Bryson? New students or continuing? They're not there. Okay.